You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So, a few weeks ago now, the Nobel Prize in Physics was awarded to 3 people on their work on black holes. This is really cool. I mean, I think black holes are some of the most interesting things in science, but black holes weren't always in the mainstream science world. For a long time, most people didn't even believe that they existed. So today we're going to dive into black holes and tell you the story of how they went from fringe scientific concept to playing a main role in this year's Nobel Prize. And of course, we'll get into what the Nobel Prizes were all about. So as you may expect, our story starts with Albert Einstein. Nothing like black holes was ever imagined until Einstein's theory of general relativity. So in this paper in 1915, Einstein describes gravity as the effect of space-time itself curving around massive objects. So the main meat of the theory boils down to what we call Einstein's field equation. Basically, on one side of the equation, we describe matter and energy in a system, and on the other side of the equation, we see how space-time curves around that matter and energy.
And in that paper, he has the things we call the field equations, and he discusses some of their approximate solutions and things like this, but there was a ton of stuff that hadn't really been fleshed out about that theory yet. A lot of its consequences weren't known. And the first exact solution to these equations that actually wound up predicting the existence of black holes wasn't found by Einstein himself, but by a different guy named Karl Schwarzschild, who was an astronomer and mathematician. And he happened to be in the trenches of the Russian front of World War I at the time. So I don't know how this happens, but he's fighting this war, and he somehow gets his hands on a copy of an issue of this journal called The Proceedings of the Royal Prussian Academy of Sciences. And in that issue of that journal, there's a brief account written by Einstein describing the new theory of general relativity. So the theory's a month old. This astronomer is in battle and combat, and he's got this one journal article, and he starts instantly figuring out some of the most important consequences to general relativity. It's pretty remarkable. And what he did is he considered a point-like mass. So just imagine there's a point in space and there's some mass at that point. And he calculated, using Einstein's equations, what the geometry of space and time would be everywhere around that point in space. If you go far enough away from that point mass, it behaves, asymptotically identical to what Newtonian gravity predicted. So everything's pretty normal if you get far away from the mass. But as you get closer and closer to that point, it gets weirder and weirder. So Schwarzschild writes to Einstein describing the solution he found, and Einstein wrote back. And he also presented Schwarzschild's result on behalf of Schwarzschild at a meeting of the Prussian Academy. And in early 1916, Schwarzschild wrote 2 papers about this, and then he dies in March. So he never really got to see the fruits of his labor. But in these just few months, this 4-month period between when he hears about general relativity and he dies 4 months later, not from the war, but from some sort of skin disease, he puts out the most famous solution in all of general relativity and writes 2 papers about it. It's pretty spectacular.
Makes us all look bad, yeah.
Yeah. What 4 months have you done anything that important, inshallah? I haven't done anything like that. So perhaps the weirdest feature of Schwarzschild's solution to these equations was that he showed if the mass was really, really very concentrated, it would be surrounded by a region where space and time were infinitely curved. So this means that nothing can ever cross through this boundary. Even light could never penetrate out of this surface of infinite curvature that would surround this point.
So general relativity describes gravity as, space-time curving around mass. And so if your mass is like really, really in a tiny area, space-time has to curve really dramatically to curve around that tiny area.
Yeah, that's exactly right. So if you take a big everyday object like a planet or a star, that object's too big to ever generate this infinite curvature that Schwarzschild was talking about. But now let's say you took something like the sun, which is 700,000 kilometers in radius in the real world, and let's say you squeezed it down into only a few kilometers. Then it would get strong enough in its curvature of space and its effects of gravity to create this infinite curvature around it. And we call the radius that infinite curvature appears the Schwarzschild radius. We still call it that to this day.
Yeah, I guess something that I find interesting is that, it doesn't have to be like a particularly crazy mass to be able to produce one of these. It can be like the Earth's mass, if compressed into a small enough space, would also do this.
Yeah, any amount of mass, or just about any amount of mass, if you compress it enough, will create one of these black holes. So with the sun, it has to be compressed to a radius of 3 kilometers. With the Earth, it would take a radius of about a centimeter, so like a marble size. If you took a speck of dust, you could squeeze it down, and small enough, you'd make yourself a black hole.
With the caveat also that black hole would probably evaporate very quickly, but we'll get into that.
That'll be next episode. All right, so Schwarzschild's solution was certainly very interesting, and it had this weird feature, and people appreciated that even early on. But I don't think any physicists really thought that black holes would exist. They didn't even have that word for them yet. It seemed like a really weird thing, and probably not something that you'd find in the real world. After all, just because a theory's equations allow for the possibility of something doesn't mean that something necessarily exists in the real world.
Maybe there are just so many solutions to Einstein's equation that this particular one that would produce a black hole doesn't have to happen.
Yeah, and maybe there's just something about the laws of physics that make it really, really unlikely or even impossible that you would ever get the kind of densities of matter it would take to make a black hole. So maybe in principle, if that ever happened, you'd make a black hole. But that's never happened in our universe. That would have been the sort of thing I think a reasonable person in 1920 or 1930 might have been saying. So it was in the 20s and 30s that physicists began to figure out how stars work and evolve. And this would ultimately lead to important understanding of black holes. So in particular, in 1920, the English astronomer Arthur Eddington wrote this book called The Internal Constitution of Stars. And he basically laid out the main principles. He said, well, on the one hand, there's gravity that's trying to squeeze a star together, make it smaller. And then its nuclear fusion is producing energy and pressure that pushes against the gravity. And a natural equilibrium tends to form between gravity pushing in and fusion pushing out. Now, Eddington realized that the nuclear fuel that powers stars will eventually run out. It will only last for a certain length of time, depending on the kind of star and how hot it is and how big it is and things like this. And gravity wouldn't. So gravity lasts forever. We don't think gravity ever runs out of fuel. So if you wait long enough, you would think that gravity will overcome the power that fusion can produce. But he wouldn't say what would happen then. We now know that what happens is those stars collapse and they form more exotic objects. But Eddington wasn't willing to speculate. In his book, he says, quote, one could make many fanciful suggestions as to what will actually happen at that point in time, but he wasn't prepared to make any of them. So decades passed, and it was figured out that sun-like stars would eventually collapse to become exotic stars called white dwarfs. So white dwarf has a mass of about the sun, but the size of about the Earth. So a much, much higher density material made of things like carbon and oxygen and things like this. And even bigger stars with masses up to a few solar masses would collapse to even smaller things. Stars we call neutron stars. A neutron star has a mass of about the sun, but squeezed into a volume the size of a city. So spectacularly dense material.
And some physicists at the time argued that even neutron stars could collapse down even more into more dense objects. So here we see the seeds of people getting a little more comfortable with the idea that maybe at the end of a star's life, it could become a black hole by just collapsing into the smallest, most dense possible state.
It's still a super controversial idea. I don't think anyone's sure that black holes exist or even willing to say they think it's likely. It's still a far out idea, but it must have been hard to not at least wonder about whether these big stars might form black holes. Throughout this whole time, despite the fact that everyone agreed Einstein's general theory of relativity was really important and really interesting, not many physicists really focused on it in their research. There weren't many ways to test it in detail. There weren't many predictions it made that, had observational consequences. And frankly, it's a really difficult theory to work with. It's really, mathematically sophisticated. And for all these reasons and maybe others, it wasn't until the late 1950s that a critical mass of really smart, capable theoretical physicists started to tackle the hard problems of general relativity. And we call this the golden age of general relativity. So like, for example, Roy Kerr in 1964 found solutions that are kind of like Schwarzschild's black hole solution, but describing a black hole that's rotating. That is something they didn't know how to do until 1964. Also in 1958, David Finkelstein used the equations of general relativity to show that black holes are surrounded by something we call an event horizon. So this is a boundary beyond which no events of any kind can affect an outside observer. Essentially, the idea is that everything inside of the event horizon of a black hole is entirely causally disconnected from everything in the universe outside of that boundary. It's really weird and really interesting. And then in 1965, Roger Penrose used the same equations, these equations of general relativity, to show that if a collapsing star is massive enough, then it is guaranteed to form a black hole. He laid out the argument for this in a short little paper, it's 3 pages, called Gravitational Collapse and SpaceTime Singularities. In this, he introduced and used mathematics that was totally different from anything Einstein had used, but essentially he found these other new ways to manipulate the formulas of Einstein to demonstrate things that Einstein had never been able to figure out, even about his own theory. This paper earned Penrose half of this year's Nobel Prize in physics. The award was given, quote, for the discovery that black hole formation is a robust prediction of the general theory of relativity. So that's all great from a theoretical perspective, but there was still no evidence that black holes really existed in 1965, but that would gradually change over the decades ahead. After all, you can't see a black hole, so it's not the easiest thing to point your telescope out and detect. But we can see their gravitational influence on any matter that might happen to be nearby a black hole. Let's say there was a black hole and there's some matter nearby that black hole, maybe some gas, or maybe there's a star nearby that the black hole could start pulling mass off of. That matter would fall towards the black hole, and as it falls closer, would be accelerated to nearly the speed of light. It kind of in spiral towards the black hole, like water flowing down a drain. As this acceleration happens, the matter moves faster and faster, causing it to be heated to millions of degrees. And if you take ordinary matter and heat it to millions of degrees, it radiates a ton of light, in particular very high energy light, like X-rays. And that brings us to this particular star called Cygnus X1. So today we know that Cygnus X1 is actually a black hole. It's about 15 times as massive as the sun and is gravitationally bound to a second star, a blue supergiant star. And the whole system's like 6,000 light years away from us. So in the Milky Way, but not particularly nearby in the Milky Way. So in 1964, this object was detected. And then in 1970, observations started to reveal that it emits bright and short flashes of X-rays, multiple times every second. These very short bursts tell us that the region of space that emits these flashes has to be very small. After all, to produce a coherent 1 second burst of light, has to come from a region less than 1 light second across, or 100,000 kilometers or so. So whatever was making these flashes of light had to be really compact, and turns out a black hole. In 1971, it was discovered that Cygnus is gravitationally bound to this companion blue supergiant star, about 20% of the distance between the Earth and the Sun away. And that star was way too big to be producing the X-ray flashes, so they knew something else had to be going on. But instead, what we've deduced is that the gas was being ripped off of that blue supergiant by the black hole, forming a disk of hot matter around the black hole, which is falling inward and being heated to millions of degrees and producing the bright flashes of X-rays.
Yeah, I feel like there are some really beautiful artist renderings of this kind of image.
Yeah, if you Google image Cygnus X1, you will not be disappointed. So in 1974, Stephen Hawking and Kip Thorne made a bet about Cygnus X1. Hawking bet that it probably wasn't a black hole, and Thorne said it probably was. And Hawking eventually conceded the bet, but not until 1990. In the late 1970s, though, I think among most of the people who were invested in this particular question started to become convinced that Cygnus X1 really is a black hole. Based on the ages of nearby stars, it seems like Cygnus X1 is probably about 5 million years old, and it would have formed in the collapse of a star that was about 40 or maybe a little more times as massive as the sun. That original star lost most of its mass, probably as part of a stellar wind, when it was transforming into a black hole, leaving only a 15 solar mass object behind.
So there we have it, the first known black hole. Being a young person myself, I definitely take for granted that I've grown up just sure that black holes exist, but this really was a big moment in science and a turning point in terms of our understanding of these very special objects.
So astronomers have discovered another totally different category of black hole as well. These are supermassive black holes. They're millions or billions of times as massive as the sun. It turns out that these sorts of supermassive black holes are found in the cores or centers of most galaxies, including our own. In the core of the Milky Way is something we call Sagittarius A Star. In researching for this particular episode of this podcast, I found that the star in the name Sagittarius A Star was coined in 1982 by a radio astronomer named Robert Brown. And he did it because he thought that this particular black hole was exciting, his words. And stars are used to denote atoms in excited states. So he was basically making a physics pun by calling it Sagittarius A Star. I never heard that before. So I said before that Roger Penrose got half of the 2020 Nobel Prize in physics for his work on black holes. The other half of that same Nobel went to a pair of astronomers for their discovery of the black hole at the center of the Milky Way, Sagittarius A Star. So this is Andrea Ghez and Reinhard Genzel. Genzel and Ghez did this by studying the precise orbits of stars that are really nearby Sagittarius A Star. They did this over a period of many years, more than a decade. And ultimately from this, they were able to determine the mass of the black hole itself and placing an upper limit on its size.
So that's the story of how black holes went from weird fringe scientific idea to really taking a main stage in physics. And, they've even made their way into popular culture nowadays with movies like Interstellar.
They're definitely real. They're definitely produced from massive stars, and they're definitely supermassive black holes. They definitely merge into each other. I mean, all these things have moved from speculation to pretty clear scientific fact.
So now let's move on to thinking about what it would actually be like to be close to a black hole. Let's imagine that the sun in our solar system was replaced by a black hole of the same mass. What would it be like here on Earth? Well, of course, since there's no sun, it would be very dark and nothing would be able to sustain life. But aside from that, the actual orbit of the Earth wouldn't change. Since the force of gravity felt by the Earth is only really dependent on the mass of the sun and not what shape it's in, the Earth would actually stay orbiting in the exact same way it is now.
But now you can imagine what it would be like if you got in some sort of spaceship and went, near the black hole, maybe went in some sort of orbit around the black hole, much closer than the Earth. So let's start out at a radius of 10,000 kilometers. Okay, so this is pretty close to a black hole, but it's a long way from its Schwarzschild radius. This is about 3,000 times bigger than the Schwarzschild radius. So, you're in the vicinity of a black hole, but you're not like pressing up against its event horizon or anything. But even at this distance, even at 10,000 kilometers, you're going to notice there are different amounts of force of gravity on different parts of your body. So in particular, if my left side is facing towards the black hole, my left arm or my left earlobe or something will feel more gravitational force than my right arm or my right earlobe, just because it's, my left side is closer to the black hole. And this will result in a tidal force that kind of pulls my body apart. Now, the kind of tidal force we're most familiar with is just the force that makes the ocean tides, high tide, low tide, things like this. And this all just comes from the gravity of the Earth's moon. Here you have an effect that's much, much stronger. So whereas the Earth's moon can slightly deform the shape of the Earth by pushing water towards and away from the moon, the idea here is that my left and right sides will get kind of pulled apart from each other from the tidal forces of this black hole's gravity. So at a distance of 10,000 kilometers, though, the tidal forces aren't that severe. It's about a tenth of a G force. So you would definitely notice that, but it wouldn't be, you'd be okay. But now let's get closer. Let's go from 10,000 kilometers to 1,000 kilometers, or about 300 times the Schwarzschild radius of the black hole. Here, you got a much bigger problem. You've got maybe 100 or so G's of force, tidal force, tearing you apart. And this is definitely fatal. The human heart only generates enough pressure to get blood to the brain for 10 G's or less. You would definitely pass out almost instantly, or maybe, almost instantly. And I don't even know what else would happen. But at 100 G's, your body would be in bad shape. But let's say somehow, I've got a body of steel now or something, and I'm a robot, and I can handle 100 G's. So now I go to 100 kilometers, so 30 times the Schwarzschild radius. Here, the net force is like 10,000 G's. So I don't know how you'd construct anything that could remain intact under these sorts of conditions. Not only would my robot body be torn to shreds, but the spaceship itself. And it would just pull everything in lines that point directly into the center of the black hole. So before, my left and right ears were kind of being pulled apart a little bit. Well, now I've taken my whole ship and everything, and I've just stretched it in the direction pointing at the black hole, taking any piece of matter and making into a long strip extending into the event horizon. We call this spaghettification, because you basically take any sort of shape and the tidal forces of gravity stretch it into long strips pointing in towards the black hole. So in addition to these powerful tidal forces you would experience in the proximity of a black hole, the presence of the black hole also impacts how time passes in the nearby space. Far away from a black hole, time passes normally, but as you get closer, the changes become more and more noticeable.
So more specifically, the closer you are to a black hole, the slower time moves for you. If you are, for example, 100 kilometers from a black hole, an hour for you would take about an hour and 2 minutes for someone far away. So a small effect, but definitely noticeable. But if you're even closer to that black hole, say 100 meters from the Schwarzschild radius, an hour for you would take 31 hours for the person far away. And if you were to actually reach the Schwarzschild radius, that hour would take an infinite amount of time according to the other person. So if you spend an hour really close to the black hole and then travel back to meet your friend far away, your clocks won't match and your friend will have aged more than you.
Okay, so let's say now that you're not in a spaceship or you're not in a propelled spaceship anyway, and you're just going to free fall into a black hole. So I'm just going to take you from some distances, drop you and let you fall under the influence of gravity towards a black hole. And let's say you send out a signal of light, let's say at a rate of once per second. So 1 hertz frequency light, just flash, flash, flash. Because of the effect of the time lapse, an outside observer, so somebody away from the black hole watching the light come flashing out, sees these signals arrive from you less and less frequently as you get closer and closer to the event horizon. So to such an observer, you seem to be slowing down as you approach the event horizon. Now, you don't experience that. Time isn't doing that for you. But to that outside observer, you seem to be kind of slowing down the closer you get to the event horizon or the Schwarzschild radius, and those flashes of light come less and less frequently. In fact, to that outside observer, it turns out that it will take an infinite amount of time before they'll ever see you cross the event horizon because of this time lapse effect. Furthermore, the light signals that they see are also being stretched by this phenomena we call gravitational redshifting. So essentially, the light has to give up some of its energy to escape the gravity of the black hole, and this stretches their wavelength or increases their wavelengths and decreases their frequencies, causing these particles of light to carry less and less energy. So from the outside perspective, not only do you slowly send less and less signal out, but that signal has less and less energy. In other words, you slowly fade from view, but never cross the event horizon or Schwarzschild radius. But now from your perspective, the falling person, the free falling person, you experience falling right through the event horizon. You don't notice anything special about this point in space. Time passes normally for you. You don't notice the time lapse. For you, it's just you fall straight through the event horizon as if it weren't there. So once, as a falling observer, you've passed through the event horizon, there's no way you can ever get out again. No amount of acceleration can ever do that. In fact, the slowest rate that you can even hypothetically move towards the center of the black hole is just by free falling. That's the best case scenario. Anything else you'll do will only move you to the center faster. In fact, from a certain perspective, you shouldn't even think about your trajectory from the event horizon to the center of the black hole as moving through space. You can instead think of it as moving through time. Once you cross this boundary, space and time kind of swap roles.
Yeah, you're causally disconnected from every point of space around you.
Mm-hmm. All you can do is sit there and
move through time.
And as you do that, you get to move towards the center of the black hole. So that trajectory is through time, not through space. Which brings us to the SpaceTime Singularity of the black hole. This is the infinite density point that you find in the heart of the black hole. To really describe this object, this point in space and time, we would ultimately need a theory that goes beyond Einstein's theory of relativity, but something that can take into account the quantum nature of our universe while doing curvature of space and time at the same time. At this point in history, we do not have any theory like this. We would call a theory like this a theory of quantum gravity. We have some candidate ideas. People talk about string theory and loop quantum gravity and other sorts of ideas in this context. But I think it's fair to say we don't know how to do this kind of calculation, at least not yet. So we really don't know what goes on at that singularity itself.
So that's it for today's episode, but definitely have your eyes out for our next episode because we're going to go even deeper and talk about the quantum mechanics of black holes that we do know and that we don't know. This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.